So I wanted to make a quick video addressing a problem that you might run into in the near future when solving for efficiency, where they ask you to solve for the ideal effort force. So they'll say, find the ideal effort force, or FEI for short. So find the ideal effort force of the inclined plane. And so if they're asking for the ideal effort force, you might be thinking to yourself, well, they already gave us our effort force, didn't they? They gave us a 6.5-pound effort force. But that is our actual effort force based on our inefficient system that we are using. In an ideal world, we would assume that our IMA is equal to our AMA. As we said earlier, in theory, the IMA is equal to our AMA in an ideal world. Whereas in the real world, the AMA is always smaller than our IMA. So when we look at this effort force here, that's 6.5 pounds, that's based on the real world where the AMA is smaller than the IMA, as you can see here. So if they ask you to find the ideal effort force, they're asking you to find actually something incredibly different. They're asking you to find the effort force based on an ideal world. So in other words, we need to use our ideal effort force equation, which is where the term comes from. And so in our ideal effort force equation, we can say that ders are free, or dE over dr is equal to our FR over our FE. But in reality, it's not equal to this. It is equal to this if the effort force on bottom is the ideal effort force. And so then we know those numbers. We know that our DE and our DR is just 20 feet over 2 feet. We already wrote that in our last video, so 20 feet over 2 feet. We can set that equal to our force resistance, which is still 50 pounds. That doesn't stop being 50 pounds just because we're in an ideal world. What will change is the effort force it would take to push this weight up this ramp. So that would be our effort force in an ideal world, or FEI. And so to solve for this, all we'll do is just cross multiply and divide. We'll say 2 feet times 50 pounds divided by 20 feet. And so 50 times 2 is just 100, divided by 20 is just 5. And so we can say that our force effort in an ideal world is equal to 5 pounds. And let's actually select all of this and let's move it over to the side just a little bit so we have a little bit more room to work over here. But let's think about that for a second. What we're saying is we have two different force efforts. And so what you need to realize is that our force effort is not equal to our ideal force effort. This is the main idea I want you to take away from this video. And this is because our force effort is always going to be greater than our ideal effort force. And this is because our force effort is equal to our ideal effort force, or our FEI, plus friction. And it's more than friction, as we've said several times. I can't stress that enough. It's not just friction. It's other things like misdirection of forces and other things too. But let's just say it's friction just to keep everything simple. And in reality, in the real world, so in reality, friction does not equal 0. Whereas in an ideal effort force world, we can go ahead and assume that friction does equal 0. And that is the main difference between the effort force and the ideal effort forces. Is in an ideal world, we don't have to deal with things like friction, and so we can set these equal and we end up with this ideal effort force that is always smaller than the actual effort force that we'll experience in the real world.